Today we're going to talk about polyprotic acids. The prefix poly means many, protic refers to protons. So polyprotic acid has two or more ionizable hydrogens. And these will ionize in successive steps. So we can look at the example of sulfurous acid. It will lose one of its ionizable protons to form hydrogen sulfide ion, and there's an equilibrium constant for that. There's another equilibrium where hydrogen sulfide loses a hydrogen ion and becomes sulfide ion, and that has a different equilibrium constant. So each step has its own Ka. The second Ka is always much smaller than the first Ka. It obviously couldn't be bigger, right? So why is the second one smaller? Well, in the first step, we have a hydrogen ion, a proton, positive charge, leaving a neutral molecule. Bless you. In the second step, now we have a negative anion that is losing a positive charge, right? And so that is just electrostatically more difficult. And so this is less likely to leave than the first one is. These are some common polyprotic acids and their ionization constants. So they're listing Ka1, Ka2, and Ka3. There are some triprotic acids. The first one here on the list is sulfuric acid, which hopefully, is familiar to us and we recognize, but isn't sulfuric acid a strong acid? Well, yes, it is. Its first ionization is strong. So sulfuric acid, dissolve it in water, all the sulfuric acid molecules lose one hydrogen ion and become hydrogen sulfate. But the second ionization is weak, and so there is an equilibrium constant for that. So a lot of these we've heard of. In fact, I think all of them. We've used oxalic acid. We're going to use it today. Sulfurous acid isn't as common. Phosphoric acid, citric acid, ascorbic acid, carbonic acid. So this is a useful table if you need Kas for these different acids. So how do we find the pH of a polyprotic acid solution? Well, the first Ka is much larger than the second or the third, so the amount of hydronium ion formed from that first ionization is much larger. And then the hydronium that does get formed in that first step actually inhibits the formation of hydronium in the second step. So we treat most polyprotic acid solutions as if the first step was the only one that contributes hydronium ion. We know that it isn't, but the other steps are so small that we can ignore them. A major exception and something you need to be keeping in your memory is if we have a dilute solution of sulfuric acid, then we cannot ignore that second step. So let's look at this one. This is a solution of carbonic acid. We are asked to find the pH. We're given the concentration of acid, 0.050 molar, and we're given the two ionization constants. If we look at these, this is 10 to the minus 7, and that's 10 to the minus 11, right? That's differing by a factor of 10 to the 4, 10,000. That's huge. So what we're going to do is we're going to write the equation, chemical equation for carbonic acid losing a hydrogen. Oops. So at H2CO3, and that's going to lose one hydrogen ion to form hydrogen carbonate ion. We need to make an ice table. make our ice table. We are given the concentration of H2CO3. This is the initial concentration. So I'm going to write that in here under H2CO3, 0.050 molar. Doesn't say anything about hydronium ion or hydrogen carbonate ion. What are the initial concentrations of these guys? 0. So hydrogen carbonate ion is definitely 0. Hydronium ion technically is 10 to the minus 7, right, because that's neutral water, but that is so small that we can consider it to be 0. And then we're going to look at how are these things changing as this reaction proceeds. Well, on the right side, we're starting with 0, so these can only increase. So this will be plus X and plus X. And then this one will decrease, minus X. In acid-base ice tables, the coefficients in this balanced chemical equation are always 1. Right? So then this is plus X, that's minus X. Just something to be watching out for. The exam coming up is on chapter 17, but also on chapter 16. And if you remember back in chapter 16, there were a lot of things where the coefficients were not 1, right? And so then if we're looking at the changes, we have to consider that coefficient. If this was a 2 here, then it would be changing by 2x. And then when we write the equilibrium expression, we have to square things, right? So just watch out for that, because we kind of get lulled into complacency in this chapter where we don't have to deal with it. So then we'll add the top 2 rows to get our equilibrium, 0.050 minus X, X and X. So this is Ka1, where carbonic acid is losing its first ionizable hydrogen or proton. So we've got the concentrations of the products divided by the concentration of the reactant. We've done this several times, right? So we're looking at the first ionization, so we're going to use Ka1, 4.3 times 10 to the minus 7, and that will be equal to, and we're going to plug in our expressions from the equilibrium row. So we've got X times X, X squared, divided by the concentration of carbonic acid, which is 0.050 minus X. And then there are 2 ways you can solve this. You can do X as small, or you can use the solver on your calculator. Personally, I think, especially if you're a little iffy with math, I think using the solver is the most straightforward way. And if you have not learned how to do that yet, I would be happy to show you. Once you see how it works, it's almost impossible to forget. I mean, it's very intuitive. And you just plug it in just as it looks, and it tells you what X is. I mean, how wonderful is that? If you're good at math, and you can just rearrange things in your head, some people can do that. It might be faster to use the X as small approximation here. But if math is not your strong thing, don't bother. I'm just going to do this to illustrate it for anyone who's interested. X is small means that this is so small that it goes to 0. Subtracting X from 0.05 just doesn't matter. And so then rearranging this, X is equal to the square root of 4.3 times 10 to the minus 7 times 0.050. And again, this is only a shortcut for people whose brains work a certain way. And that has nothing to do with how smart you are. It's just how your mind works. And so this is 0.00014666. Okay, I'm hoping somebody did it with a solver. What do you get with the solver?
1464.
0001464. See how close those are? Yeah. Just because this is what you're supposed to do, I'm going to take my number here and I'm going to divide it from what x was being subtracted from, just to make sure that my approximation is valid. Divide it by that, multiply by 100, and it's 0.3%. If it's less than 5%, x is small can be used. If it's more than that, you can't do x is small. I'm going to go ahead and use this x is small value because I'm pretty sure that's what the book used to get its final answer, and this way it'll match up perfectly. So what does x represent here? It's the H plus concentration, right? So the hydrogen ion concentration is 0.0001466. How do we find the pH? The negative log of that, right? Negative log of the hydrogen ion concentration. Negative log of and my calculator shows me 3.8339. When we're doing ice tables, it's almost always two significant figures. And so you can just look at the Ka values, the initial concentration, whatever those sig figs are, you can just safely do that many sig figs in your answer. The one tricky thing is with pH and sig figs, right? This 3 represents the decimal places. If we write it in decimal notation, the number before the decimal point is the number of zeros in front of the number. So all the sig figs come after the decimal point. So if this has 2 sig figs, then this has 2 decimal places. I won't try to trick you with that on an exam, but it is confusing to some people. Why did you round it that way? That's why. Any questions? We don't need to use the Ka2 because it's so small. Yeah. Yesterday in lecture, honestly, I hadn't looked at my slides, these slides, since spring of 2023, right? This makes it more interesting. No, I just didn't bother. I was lazy. So I got to this slide, and it's like, I couldn't remember, was I supposed to do both of them just to show you or not? So I did both of them. And then I realized in a slide coming up, there's another question where we have to do the second part, and I really didn't need to do it right away. So now I know we'll do that part later. Yeah. Any questions? .83, nice. Okay, find the pH and sulfate ion concentration of a 0.0075 molar sulfuric acid solution, Ka2 equals 1.2 times 10 to the minus 2. So there's a couple of things that make this a little different. It's only giving us Ka2, it's not giving us Ka1. Why? Because sulfuric acid is a strong acid. The first hydrogen ionizes completely. So easy to forget that. If you go looking for the first Ka, you're not going to find it. If you look in this table, then you'll be like, oh yeah, that's right, that one's strong. If you look somewhere else, you may not realize that. Okay, so It's a strong acid in the first ionization. So let's think about what's happening here. We've got sulfuric acid, H2SO4, and that will ionize completely into hydrogen ion and hydrogen sulfate ion. Okay? So here we're starting with 0.0075 molar sulfuric acid. So all of that reacts, and so the concentration of HSO4 is 0.0075, and the concentration of H plus is also 0.0075. Does that make sense? Because it all reacts. I saw some puzzled looks. So let's just make kind of a nice table for this. Initially, we would say, well, this is starting with 0.0075, and that one's 0, and that one's 0. The change here, this is more of a stoichiometry problem. It's not an equilibrium problem. All of this is going to react. So that's going to change by negative 0.0075, and we're going to end up with 0. This is going to change by plus 0.0075. And this will change by plus 0.0075. And I gained a 0 there. Gotta watch out for stuff like that. Does that make a little more sense? Yeah. You see how that works? Yeah.
You know when an equation's like an equilibrium or not? You just have to know like based off the formula.
Yeah, how do you know if it's an equilibrium or not? Is that basically your question?
Yeah.
So most of the things we're talking about in these chapters are equilibrium. If it's an equilibrium, it has an equilibrium constant. So the constant for this would be Ka1. It's not given to us. If we go look for it, we can't find it. In that table, it just says strong instead of an equilibrium constant. So that's how I know that this is going to go to completion. This is not an equilibrium. Other things that you might see that way would be any of the strong acids. This is the one strong acid that's kind of weird because it has two protons. It's only strong in the first one. All of the other strong acids are monoprotic. They just have the one hydrogen, and so they're just going to ionize completely. And strong bases also dissociate completely, and so they are not in equilibrium. Does that answer the question? Yep, good question. Okay, so this is actually a simple thing, right? But it's kind of confusing because it's different from the pattern of what we've been doing for everything else, right? And so this is where we have to, pull together different ideas, which reminds me of a podcast that I listened to recently. There's a great podcast called The Hidden Brain. I highly recommend it. They had an episode recently about memory and learning, which was really pretty fascinating, and I found to be very applicable to learning, material in a college class or, learning content of any kind like that. And one of the things they were talking about is we often mistake familiarity with knowing or having learned something. And so it's pretty easy to sit here and watch me do ice table after ice table, and you're like, oh yeah, I see how that works. I'm really familiar with that. You go to study for an exam, you look over your notes. Oh yeah, remember that. And then you take the exam, and you're like, right? And things don't go very well because you were familiar with it, but you hadn't actually learned it. So an example is this podcast, right? I can tell you I heard this great podcast, and I don't know the basics of what they said. I did not study it. I did not learn it. I just listened to it once. So I can share a couple of things about it, but I haven't learned it, so I can't explain the whole thing to you, right? I would have to go back and look at it multiple times and think about it, maybe ask myself some questions before I would be in a position where I could teach it to you, the whole podcast. So all I'm doing is saying, hey, this was good, go listen to it. So how does that apply to learning something like this? In order to learn this, you actually have to interact with the material. You have to do problems. That's why I assign homework for you. You have to do the problems, you have to wrestle through them, right? You haven't really learned something until you're able to explain it to someone else. So, well, I don't have anybody who's willing to listen to me explain diprotic acids. That's fair, right? Well, you can write out explanations, right? And so one of the things about making notes for yourself is going back and just trying to write out from memory, explaining things that really helps solidify it in your head, right? Working a problem and not just following the pattern of a similar problem, which I think it happens a lot because you can go online and there's all kinds of videos and helpful sites and stuff, and they'll show you how to do a problem. Well, if you just follow along as they do that, it's not going to help you very much. You need to be able to do it without having someone next to you, video or otherwise. So what I would encourage you to do, if you haven't already been doing it, I do a lot of examples in class, right? And so hopefully you're taking notes, and so you're writing all over your copy of the slides. But there's another copy of the slides available online on Canvas. And you don't have to print it out if you're using the paper ones. You just need to pull it up so you can look at it. You want to be able to look at the question without everything that you wrote down during lecture. You should be able to go back and do these problems without looking at anything except that page of useful information and periodic table that you'll have for an exam. Does that make sense? You go back and do that, and I would recommend doing that like later today after lecture, right? Go back and do all the problems that we did in lecture, then go do your homework. Because this will help get everything entrenched in your mind, and it'll make the homework easier. Anybody have any questions about that? It was kind of a spontaneous how to learn lecture. Okay, so let's just go forward here. Okay, so the first hydrogen comes off completely, and so these are now our initial concentrations for the second equilibrium. So the second equilibrium is the HSO4 losing a proton. This one is equilibrium because there's a Ka. This is not a strong acid. So ice table. ICE. What's the initial concentration of HSO4 minus? It's this 0.0075. What's the initial concentration of H plus? Also 0.0075. How about sulfate ion? 0. So now we can see why this equilibrium doesn't contribute a lot to the overall concentration of hydronium ion. Because here we're starting out with a bunch of hydrogen ion. That's the product in this equilibrium. And so that's going to affect the position of this equilibrium it's not going to go as far as it would if it started at 0. It can't start at 0 because there's hydrogen ions that came off before this even got to do anything. So this one is 0, and so that one can only go up, so this side must be plus x. There will be times when you're not sure which side is plus x and which side is minus x. But remember, the double line here, the equilibrium arrow, everything on one side has to have the same sign for x. So here both of these have to be positive, and then the other side has to be negative, because it's going one way or the other. So we fill this in, 0075 minus x, 0075 plus x, and x. Well, I'll just go ahead and do it. So Ka2 will be that, right? The products divided by the reactant. And then we take these guys and we plug them in. So we've got 1.2 times 10 to the minus 2. That's going to be equal to 0.0075 plus x times x divided by 0.0075 minus x. Go ahead and plug that into the solver. I'm going to show you what happens when we try x is 0 on this one. So x is 0 means we're going to call both of those 0. And then these numbers cancel out, and we're like, oh, that is so much faster, right? We end up with x being equal to 1.2 times 10 to the minus 2. But we have to check. Take this and divide it by 0.0075. 1.2 times 10 to the minus 2 divided by 0.0075 times 100. 160%. Is x small? No, not even close. X is not small. Rewind. So x is not small. We have to use the solver or quadratic equation or some such silly thing. Oh, cool. I still have it in here from yesterday. So, oops, I wanted blue. So what I get when I solve that is that x is equal to 0.003854. Did you get that? Anybody? Okay. So we're supposed to find the pH. Is this the hydrogen ion concentration at equilibrium? No, it isn't. It can be, if you're not really on top of things, you're like, oh, there's x, negative log of x, bang, there's my answer. Not this time. The hydrogen ion concentration is 0.0075 plus this number, right? So let's put that over here. H plus is 0.0075 plus 0.003854. .0011354. So pH is the negative log of that. .9449. And, this has 2 sig figs, that has 2 sig figs. It's reasonable to round this to 2 sig figs, which is 2 decimal places in a pH. The other question is, what's the sulfate ion concentration? Well, the sulfate ion concentration is X, right? So the sulfate ion concentration is equal to X. So we could round that to 0.0039. Any questions? So there was a bunch of different things that happened in that problem, right? It wasn't just write a nice table, solve for X. None of those pieces, though, is terribly difficult, right? This is something we learned how to do in Chem 1A, but we didn't think about it that way. We didn't talk about it that way. But that's, once you see what's going on there, that's simple enough. We make a nice table. That's okay. And then, the H plus, well, we have to add it to this. Well, that's not so hard, but we have to remember to do it, right? And so it's easy to forget. There's lots of places where you can make just a little mistake. So they put 3 sig figs on this one. I have no idea why they did that. It's okay. Okay, so let's look at the concentration for the anions for a weak diprotic acid. If we're calculating the pH, we can ignore the second ionization. If we're trying to find this anion concentration, then we can't ignore it, and we have to do the whole stupid thing. So if we want to find HX minus, the first ionization product, then we calculate hydronium as concentration just like we do for a weak monoprotic acid, and the concentration of HX minus is the same. If we need X2 minus, then we're going to use the results of that first ice table and do another ice table. So let's look at that. So this is the continuation of that previous problem. So look back in your notes. Is this the right number? 001666? There was one that was 16. Let me go back in my calculator. Oh, it's 1466. So this is the result of us finding the hydrogen ion concentration so we could get the pH of this carbonic acid solution. So a couple of slides back, we worked that out. We did not do the second ionization because that equilibrium constant is so small that it wasn't going to matter. But now we want to know the carbonate concentration. So if we were starting from scratch here, if we hadn't already done that problem, we'd have to do an ice table here to get this number. We already did that, so we don't have to do it again. So we're just going to look at the second ionization here. Is there one more zero? Yep, you're right. Thank you. That would mess things up. ICE. So the result of the first ionization is that the hydrogen ion concentration was this number. 0.000166. No, boy, this is, let's try that again. 0.001466. There we go. Let's just write that equation up here so we can remember what we're doing. So this was the first ionization. We did the ice table. We found that the concentration of hydrogen ion was this number, and that HCO3 minus was also that number. Is everybody cool with that? So our starting concentration here is not 0.05, it's not 0, it's the same number, because we get one of these for every one of those. So this is also 0.000146. What's the carbonate ion initial concentration? 0. Okay, so this side's going to be plus x. This side's going to be minus x. 0.000146 minus x. Ka2 equals H plus times CO3 2 minus divided by HCO3 minus. Here's our ionization constant, 5.6 times 10 to the minus 11, and that equals 0.000146 plus x times x divided by 0.000146 minus x. That can go straight into your solver. I'm just going to look at x is small. So if x is small, then adding it to that number doesn't matter. We can consider that to be 0. Subtracting it doesn't matter either. And then those two numbers cancel out. And x is equal to 5.6 times 10 to the minus 11. Well, with the sulfuric acid, that didn't work so well. So let's just check this to make sure it's going to be okay. 5.6 times 10 to the minus 11 divided by 0.000146 times 100. Yeah, that's less than 5. 0.00004%. Is X small? X is super small. I'm just curious, what number did you get from the solver? 5.99 times 10 to the minus 11. Yeah, really close. So when we were calculating the pH, the hydrogen ion concentration at the end would be this number plus this tiny number, and it ends up just being the 0.000146. That's why we could just use this for the pH and not worry about this second part. But here, we're trying to find the carbonate ion concentration, which is X. So the carbonate ion concentration equals 5.6 times 10 to the minus 11. If you use the solver, you'd come up with 6.0 times 10 to the minus 11. On an exam, only one of those would be present as a multiple choice correct answer. And so if you get this number and that's the choice, we should understand enough about uncertainty and sig figs to realize that that's the number we should choose. Yes?
My solver at 5.59.
5.59. Okay, I probably misheard. That makes more sense. 5.59. Yeah, so then we've got no trouble at all, because that would round to 5.6. Any questions? That would be molar. .6 times 10 to the minus 11. So let's look at what's happening when the polyprotic acid dissociates. I think this is citric acid. Don't quote me on that one. So we've got a diprotic acid. It loses one hydrogen ion to make hydronium and this anion. We could do the calculation with its equilibrium constant, and we find that the hydronium ion produced here is 2.8 times 10 to the minus 3. That then is the starting concentration for the next ionization, so that inhibits it. We do that calculation, we find that the hydronium ion concentration from the second step is 1.6 times 10 to the minus 12, a really small number. Total hydronium ion concentration is the sum of those two, which, because this is so small, it just ends up being the first number. So the amount of hydronium ion from the second step is insignificant. The only time you skip that is a dilute solution of sulfuric acid. Only time. You have to do the second step. The concentration of that ultimate anion, the weak diprotic acid, that concentration is going to be this number, and that is equal to Ka2. That's only true when the X's small approximation is valid, but that's almost always true. If we go back to this one, so this is the second ionization of the diprotic acid, and this concentration ends up being the same as Ka2. So if this was an exam question, right, and you were really on top of things, you could just look at this and say, well, it's going to be this, because that's how it works. And if you didn't remember that, you could do the problem and still get the right answer. Yeah.
Would that work for all the problems?
It'll work for the ion, the A2 minus ion of a weak diprotic acid. So it's kind of a niche thing, right? So is that worth remembering? I don't know. That's kind of up to you. I probably, if I was taking an exam, I probably wouldn't trust myself with that. I would just go ahead and do the problem, right? So any other questions about diprotic acids?
So we're saying that the concentration of the anion of the second equation, of
Yes,
the second ionization, will be equal for the Ka.
yes, yeah. So the concentration of X2 minus, which in that example was the CO3 2 minus, for the weak diprotic acid H2X, is going to be equal to Ka2, and that's what we saw in the previous example.